Good afternoon and welcome back to the Johnson Space Center for today's status briefing on the progress of the scientific research flight, STS-107. The orbiter is functioning perfectly today, so we excused Phil Engeloff from extra duty this afternoon, and we'll press right into science. Our briefers today to talk about the research on board Columbia: Dr. John Charles, the STS-107 mission scientist; Dr. Paul Ronnie, the principal investigator for the softball experiment; and Dr. Libero Ligieri, the principal investigator for the European Space Agency Adsorption Dynamics and Rheology experiment. And we'll start off with John.
Thank you, Rob. First, let me review the last 24 hours of NASA's science payload activities in orbit. At the end of 6.5 days in orbit on STS-107, the science payloads aboard Columbia are active and are continuing to operate very successfully. The softball investigation, that is structure of flame balls at low Lewis numbers, of Dr. Ronnie commenced activities overnight, replacing the laminar soot processes investigation in the combustion module. We'll hear more on that from Dr. Ronnie here in a second. The other major experiment in the area of microgravity physical sciences, the mechanics of granular materials, has no more operations planned today, but will resume tomorrow with 3 more compressions over the course of 2 days. And in other areas of research, the animal health checks indicate that the animals are doing well, and the crew refilled the animal water containers as scheduled. The slightly elevated module temperatures have led us to ask the crew to remove the sound mufflers on the front of the animal modules, and that was done to help them be a little bit cooler. Today was a big day for the biological experiment involving the growth of moss plants in spaceflight, examining the unexpected spiral growth of moss plants in the absence of gravity. The moss growth was chemically inhibited as planned today, and then a series of time-critical fixations were underway so that the growth rate can be determined post-flight. Astroculture, the investigation with the flowers in space, the rose and the rice flower, acquired its first 2 sample harvests over the course of the last day or so of the volatile essential oils we heard about before. The microbial physiology flight experiment, studying the growth of microbes in the absence of gravity and other environmental changes in spaceflight, experienced a second jammed card tray, so they've modified the procedures to overcome that problem and will be executing the modified procedures. No data was lost as far as we know on the second jammed card tray. The bioreactor experiment growing the prostate cancer cells in the presence of bone marrow cells is continuing to show much greater growth than expected. The rotation rate of part of the internal mechanism, the spin filter, has been slowed down from 6 RPMs to 3 RPMs to try and minimize the shearing off of the outer layers of the unexpectedly large cell aggregate. So that's going well, and all the other NASA science experiments are proceeding normally. This time I'd like to ask Dr. Ronnie to talk about the softball experiment.
Thank you, John. The last 24 hours have been a great day in the history of combustion science. We've known for over 100 years that if a mixture is too weak, has too little fuel mixed with air, it won't burn. But what we've found, all knowledge that we've had up to this point has been tainted by the fact that all the experiments had been done in the presence of gravity. Gravity affects flames, especially weak ones, because hot gases rise, and that causes a certain flow field, which for most flames will cause them to extinguish. Just like if you can blow out a birthday candle or a match, even gravity, the flow induced by gravity, can cause that through a process we call natural convection. Now, by going to low gravity, we can eliminate this process, so we don't have any of this flow, and we can actually observe weaker mixtures than we could possibly observe in the presence of gravity. Yesterday, we burned the weakest mixture ever burned, either in space or on the ground. And today, this morning, we burned the leanest mixture, that is the one with the least fuel of any mixture ever burned, either in space or on the ground. Just to give you some numbers, the flame that we burned yesterday produced only 1/2 a watt of thermal power. By comparison, a birthday candle is about 50 watts. So the flame we burned yesterday was 1/100th the power of a birthday candle. The flame we burned this morning, it was 8% of the chemically balanced mixture of fuel and air. By comparison, in your car engine, the leanest mixture you can burn is about 70% of the leanest mixture of the stoichiometrically balanced mixture. So with this knowledge, we hope to improve our models of weak combustion. Why we want to know about weak combustion is because we know that if we could burn leaner mixtures, weaker mixtures in our car engines, that we could get higher fuel efficiency and lower pollutant formation. But we're limited in our ability to model that process because of all the complications induced by turbulence in a car engine and by gravity even in a non-turbulent flow outside of a car engine. Could I have the video, please? So what we've done is we've done experiments using these flame balls. These flame balls that you see here were theoretically predicted by a Russian physicist in 1944, and the first experimental observation of these flame balls was in 1984 by myself. We caught a fleeting glimpse of these in very short duration low gravity experiments done in what we call drop towers, this one at NASA Glenn. But it was only a fleeting glimpse, 2 seconds worth is all we could do on Earth. Now, by going to the space experiment, we can get, that video that you saw was actually sped up. The total elapsed time was about 12 minutes. So by going to space, we can see these long duration, low gravity flames, and we can study their structure, learn all about their properties, and compare that to our theoretical predictions of the process. And by that, build better models of the whole process. The goal is not to use flame balls in our car engines. The goal is to learn more about weak combustion so we can better model what goes on inside our car engines. I like to consider these flame balls as the fruit fly of combustion, just in the sense that people study fruit flies not because they want to breed better fruit flies, but because they want to understand genetics. And the fruit fly is one of the simplest systems in which you can do that. By the same token, this flame ball is a spherically symmetric flame. It's relatively easy to model. It doesn't move, so we don't have to worry about the time-dependent dynamics. And the chemistry involved with these particular mixtures is quite simple. So basically, if we can't model this, we can't expect to model the much more complicated processes going on inside of a car engine. So it's sort of an acid test for any model that we developed. And I say we've had 3 burns so far. It's been a great mission for the experiment to date.
Thank you, Dr. Ronnie. And Dr. Ligieri will now review the fundamental in-flight research aboard Columbia into the physics of fluid interfaces.
Thank you. I'm here as the coordinator of an European Space Agency project on the stability of emulsion. This is an application project. And the first experiment, which is performed on board the STS-107, is an integral part of this project. FACE stands for Facility for Absorption and Self-Extension. There are actually 3 experiments running. The time mission is shared between these 3 experiments, and the experiments are aimed at an investigation of specific properties of liquid interfaces, liquid surface, and in particular in the presence of surfactants. Surfactants are compounds which are used in many technologies. They are essentially soaps, but they are used in a huge number of technologies and also have important impacts in many biological processes also. For example, breathing is a physiological process in which surfactants are strongly involved. These compounds, these molecules tend to accumulate at the interface and modify the surface tension. Surface tension is the main parameter characterizing the interface. Is this parameter that makes the drops stay together, exist as drops, it doesn't spread, for example, on a solid surface. If you look at the liquid interface, you can see it as a rubber membrane, and exactly as a rubber membrane, the interface is characterized by a given tension and by a given elasticity. And the aim of the experiments, of the first experiment, is exactly to try to determine, characterize, and measure these quantities, surface tension and elasticity. The experiments are designed to study the response of surface tension and elasticity to changes of the area, so compression and expansion of the droplet area. And maybe we can have the images. When surfaces are compressed, or when surfaces are expanded, there is a movement of surfactant from or to the droplet interface. And even if surface tension itself is not as affected by microgravity, the transport of the surfactant, the way in which the surfactant moves inside the liquid, is affected by the microgravity. So microgravity provides a simplified environment in which we can study such kind of phenomena. And microgravity also provides always spherical interface, which makes easier to compare experimental results, for example, with the models, and also allow to this simplified situation, also allow to insulate some critical parameters, understand and measure it. The results are important in many kinds of technologies, from, for example, separation of oil from industrial wastewater, or the production of crude oil, design foams, design foamed materials, design foods, drugs, cosmetics, and so on, inks, pens, so many different fields. There are also, in this experiment, many technological challenges have been solved. For example, the droplet that you see on the screen is a droplet of about 1 millimeter, half a millimeter in diameter. And one of the major problems has been to control the size of this droplet very precisely. And what is also important is that this droplet is the same during all the missions. So for the mission, we are always looking at the same interface, which means that the experiments run automatically, and for all this time, the system must be under control. The experiments today are performing, I say, very well. There are two kinds of interfaces which are studied. One is a water exhaust interface. The second one, the one that you see now on the screen, is a water air interface. The surfactant is contained in the external phase. It's a model surfactant in both cases. The facility is able to change surfactant concentration and temperature. And in total, we have about 2,000 experimental runs that will be performed during all the mission. So far, we are more or less at the middle of these 2,000 experiments. We have a very high rate of success of these experiments, and the facility is performing very well. We had experienced some problem due to the high temperature in the cabin, essentially for the thermal control, but more or less we have been able to solve this problem, so we are very satisfied with what is going on.
Thank you, Dr. Legere. And tomorrow we'll hear from Dr. Nicole Buckley, who is the program scientist of the Canadian Space Agency, who will tell us about osteoporosis experiments in space, and Dr. Dag Lennerson of the Karolinska Institute in Stockholm, who will discuss the European Space Agency's Advanced Respiratory Monitoring System experiments aboard Columbia.
Thanks, John. We'll take questions here in Houston from reporters before going down to the other centers. Start off with Mark.
Thanks, Rob. This is Mark Carreau from the Houston Chronicle, and I had a few questions for Dr. Ronnie about the flame ball experiment. Could you sort of characterize this phenomena as to how big these things get, how bright they are, how long they last, and is it a trick to get them to form in microgravity, even though they form more readily than they would under gravitational forces?
The flame balls that you saw in this video were about 1 centimeter or 3/8 of an inch in diameter. They range from maybe a small, on the low end, about 1/4 of an inch to maybe as much as 3/4 of an inch in diameter. They can last, the longest one that we have burned has lasted about 20 minutes, and that's also, I believe, also a record for combustion experiments performed in space. They're actually quite easy to produce. We ignite them with a spark. You didn't see that in this video clip, but they're just ignited with a spark, not fundamentally different from the spark that ignites the flames in your car engine. And they decide on their own how many flame balls to produce. That's one thing we can't control, is the number of flame balls that we get. Once they ignite, then you see, in this case, we got 3 flame balls. After a while, because they're competing with each other for fuel, the strong survive and the weak die, so one that was a little bit weaker then started to lose more and more fuel, and it extinguished, and then another, and then finally there was one left that was able to last a lot longer than the others. In terms of then the ignition process, we can try changing the ignition energy as well as the mixture strength to get different numbers of flame balls, but basically we have to let nature tell us. For most of the cases, we'd like to have just 1 flame ball in the center, but getting 2 or 3 gives us the opportunity to look at the interactions between flame balls, which is quite an interesting subject in its own right.
And I just had a follow-up question really about how you, what the data is that you gather. Is it an image, and then do you take these later and evaluate them somehow, and what do they tell you? Could you explain that a little bit?
Sure. What you're seeing is actually a false color image taken from an intensified video camera. These flame balls are not visible to the naked eye. That's how weak they are. And the particular mixture that you saw there was in a hydrogen air flame, which does not produce any visible emission. Just like the space shuttle main engines, you actually don't see that. You see only the solid rocket motors. And we take these images. We also take data on the amount of thermal radiation being emitted from the flame. Thermal radiation should not be confused with nuclear radiation. Thermal radiation is what makes a campfire feel warm when you're standing 5 feet away from it. And we measure that. We also measure the temperatures of the gas inside the chamber. We take all of this and we compare it to our computer models of the process. And then we found that originally the models we were using, even though they were the standard ones used by many combustion researchers, were severely limited in their ability to predict this flame ball. So we've added new phenomena and tweaked some of the existing phenomena. Now we have much better agreement between the model experiment, which again we hope to use to design better car engines that can burn leaner and more fuel efficient.
Okay, let's go down to the Kennedy Space Center for questions.
Hi, this is Chris Kreidler from Florida today. I also have a flame ball question. Could you go over again what records have been made? Is there a record for duration and also for the length of the flame itself?
Yeah, I think it's pretty clear that we have the record for the weakest flame ever burned. Again, this is either in space or on the ground. About half of a watt, as compared to 50 watts for a birthday candle. The leanest mixture with the least fuel compared to the amount of air ever burned, about 8% for the mixture we burned yesterday, as compared to in a car engine where you can't burn a mixture that's less than about 70% of the chemically balanced, or what we call stoichiometric mixture. I also believe we have a record for the longest burn in space, 20 minutes, for a test that was performed, the first test that was performed yesterday also. And if there are any other, I guess you could also say maybe the most excitement by a combustion researcher. Is that a record too?
Thanks. This is Marcia Dunn of the Associated Press with a few more flame ball questions. What is the fuel you're using?
Most of the tests that were most of the tests use hydrogen fuel, simply because it's easier to get flame balls in hydrogen than in other fuels because of its diffusion properties. We also are doing some tests with methane, which is the main component of natural gas. Now, hydrogen by itself is only occasionally used as a fuel in automobiles, but the understanding of the chemistry and physics of hydrogen combustion is a necessary precursor, a building block, to understanding hydrocarbon combustion as it's used in our car engines. So again, using the fruit fly analogy, if we don't understand this part well, we can't possibly understand the big picture about combustion as it would occur in car engines and industrial furnaces. Also, I should point out that spacecraft have many sources of hydrogen in the fuel cells and the propulsion systems, and these flames actually burn, as I mentioned, weaker than mixtures could burn on Earth gravity. So we want to make sure that the criteria we use for fire safety on the ground is also applicable to fire safety in spacecraft.
In the sizes you gave a little while ago for the diameters of your flame balls, it wasn't clear to me whether that's during this flight or previous tests. The 3 runs so far for the weakest, the leanest, and I don't know if the third one ever got a record. But what are the sizes that you've seen on this flight alone? Are those the numbers you gave out earlier?
Yes, about 5 millimeters up to maybe for the biggest one that we've seen here, about 10 millimeters in diameter. The field of view in the video that you saw is about 30 centimeters, which is about 12 inches.
Thank you. And the leanest and the weakest, did I hear right when you said that even the astronauts could not have seen them taking place without some sort of magnification?
Yeah, they would not have been able to see them with their naked eye because these hydrogen flames do not produce any light in the visible portion of the spectrum, only in the infrared and in the ultraviolet. Some of the tests that we'll perform later in the mission are with methane, and those could be seen with the naked eye.
And did they have any magnification, or how did they know whether in other words, how did they know what they were doing if they couldn't see the results real time?
We're seeing the same video that we were seeing on the ground, so they were able, with this intensified video camera with a false coloring so that it makes it visible to the naked eye. That's how they were able to monitor the progress of the flames, as well as look at some of the scientific instruments to measure the radiation and the temperature of the flames.
Okay, that's all the questions from the Kennedy Space Center. No follow-ups here. We'll close with a couple of programming notes. Coming up at 1:45 p.m. Central Time, 2:45 Eastern Time this afternoon, a short time from now, we'll have an additional STS-107 science briefing with principal investigators gathered at the Kennedy Space Center for this flight. The flight day highlights themselves, all of the activity on board Columbia over the past 24 hours will air for the first time at 8 p.m. Central Time, 9 p.m. Eastern Time this evening, and will be replayed several times on the hour, every hour, for the next several hours after that. For all of the latest information about Space Shuttle and International Space Station activities, you can go to our human spaceflight website, please, at spaceflight.nasa.gov. And with that, we'll return to mission control and coverage of the STS-107 mission. Thanks very much.